Hey there! Today we're going to demystify two of the most interesting rules in all of algebra, the zero exponent and the negative exponent. Now, I know they can look a little weird at first, but stick with me and you'll see they actually follow a super simple, kind of perfect logic.
So let's just jump right in. We all know that an exponent is just a way of saying repeated multiplication, right? Like x cubed is just x times x times x. Simple enough. But how in the world can you multiply something by itself 0 times? Or, and this is even weirder, a negative number of times. It just doesn't seem to make sense, right? Well, that's the puzzle we're going to solve together today. So here's our game plan. First, we'll talk about why these exponents feel so strange. Then, I'll give you the rules in plain English. After that, and this is the most important part, we're going to dig into why they actually work. Then we'll do some practice, I'll show you a super common mistake to avoid, and then you'll get a chance to show off your new skills.
All right, first up, let's get right to the heart of why these exponents can feel a little off when you first run into them.
You know, at the end of the day, exponents are just a shortcut. I mean, it's way easier to write x to the 7th power than to write out x times x times x. You get the idea. But that very definition, repeated multiplication, it kind of seems to just fall apart when you throw in a 0 or a negative number. It's not intuitive at all, and that's exactly why we need a couple of special rules to handle them. So let's get to the good stuff, the rules. And here's the best part. Even though the idea of a 0 or negative exponent is strange, the rules themselves, they are incredibly simple. Let's break them down.
First, we have the zero exponent rule, and it's as easy as this. Any non-zero number, I don't care if it's 5 or 500 or a variable like x, if you raise it to the power of 0, the answer is always 1. That is it. 10 to the power of 0, it's 1. A billion to the power of 0, still 1.
And now for the negative exponent rule. Look, a negative exponent does not mean the number itself becomes negative. That's a super common misconception. Instead, just think of a negative exponent as a little signal that's telling you its base is on the wrong floor of the fraction. To fix it, to make that exponent positive, you just move its base to the other side. So x to the negative a becomes 1 over x to the positive a. It's basically like giving it an elevator pass to the other side of the fraction bar.
Now, you could just memorize those rules, and you'd probably be fine on a test. But math is so much cooler when you understand why things work. And trust me, these rules aren't just random things someone made up. They are baked into the logic of math itself.
Okay, check this out. This is where it all clicks. We're going to prove the zero exponent rule using stuff we already know. On the left, we use the quotient rule. Remember, when you divide powers with the same base, you just subtract the exponents. So m to the 5th divided by m to the 5th gives you m to the 5 minus 5, which is m to the 0. Okay, but now look at the right. What happens if we just write it all out and cancel? Well, any number divided by itself is just 1. Since both of these methods have to be true, m to the 0 must equal 1. It's the only thing that makes sense.
And this is just beautiful. This shows the logic for negative exponents. Just follow the pattern with me here. To get from 2 to the 4th, which is 16, down to 2 to the 3rd, which is 8, you divide by 2. To get from 8 to 4, you divide by 2 again. So if we just keep this pattern going, what's 2 to the 1st power, which is 2? Divided by 2, it's 1. So 2 to the 0 has to be 1. And what if we go one step further? What's 1 divided by 2? Well, it's 1/2. So 2 to the negative 1 power is 1/2. See, the pattern just works perfectly.
All right, theory's over. We've talked about the what and the why. Now let's get our hands dirty and actually solve some of these.
Here's a nice, clean example, just like the proof we just saw. When you see m to the 5th divided by m to the 5th, you just subtract those exponents. You get m to the 0. And what does that equal? 1. Boom, done.
Okay, that was a good warm-up. Now let's try something a little trickier. A problem where you really have to pay close attention to what that negative exponent is actually attached to.
So take a look at this. Negative 7, a to the negative 3, b squared. Now, a really common mistake here is to think that the entire term has to move. But that's not right. That little negative 3 exponent is only latched on to the a. It's got nothing to do with the negative 7 or the b squared.
So here's the deal. The a is the only piece that has a negative exponent. So it's the only piece that's unhappy and needs to move. The negative 7 and the b squared, they're perfectly happy staying right where they are, up in the numerator.
Let's just picture it. That a to the negative 3rd takes that elevator ride we talked about down to the denominator. And the moment it gets there, its ticket gets punched, and its exponent becomes positive. So now it's a to the positive third power on the bottom.
And there you have it. That's our final answer. The -7 and the b squared stayed up top. The a to the third moved to the bottom. Everything's got a positive exponent now, which means our job is done. The big takeaway here is only move the specific base that the negative exponent is directly touching.
And speaking of things being attached to each other, we need to talk about a very, very common trap that students fall into in dealing with exponents: parentheses.
This is so important, so pay close attention. On the left, we have -4x squared. That little 2 is only attached to the x. The negative sign is just kind of hanging out in front. But on the right, those parentheses act like a container. They tell the exponent to apply to everything inside. So, -4x squared means you multiply the entire thing by itself, which gives you a positive 16x squared. See? Parentheses literally change everything. You have to watch out for this, especially when you have negatives and negative exponents all in the same problem.
Okay, you've seen the rules, you get the logic, and you've seen a couple of examples. Now, it's your turn to put it all together.
Here is your challenge problem. You're going to need to use the quotient rule for each of the variables here. So go ahead and hit pause right now, work it out, and then press play when you're ready to see the solution.
All right, you back? How did you do? Let's walk through it. First, 63 divided by -7 is -9. Easy enough. For the a's, you've got a squared over a squared, which is a to the power of 0. For the b's, 4 minus 3 is 1. And for the c's, 7 minus 5 is 2. And of course, since a to the 0 is just 1, it basically disappears. So our final simplified answer is -9bc squared. Fantastic job.
So, I'm going to leave you with this thought. These rules aren't magic. They're not just something to memorize for a test. They're built on a solid foundation of logic. And when you really focus on understanding why they work, like we did with those patterns, they become something you truly know, not just something you've crammed into your short-term memory.
You've just leveled up your understanding of exponents in a huge way. So the real question is, what's the next puzzle you're going to use these new skills to solve? I really hope this helped you out. Thanks for tackling this with me today.